Okay, why don't we go ahead and get started? Good morning, y'all. Great to see everybody. So today we are very lucky to have Prahladh Harsha from the Tata Institute of Fundamental Research to tell us about multiplicity codes. So this, I think, can be viewed as maybe a follow-up to the two lectures that I gave yesterday, which were sort of like all over the place of algebraic codes. And now Prahladh is going to go a little bit deeper into one particular type of algebraic code, which I didn't get a chance to talk about at all, multiplicity codes. And unfortunately, due to visa reasons, Prahladh is not able to join us in person, but hopefully he'll be here later. Yeah, so thanks so much for coming. Prahladh, thanks so much for, I guess, staying up late and take it away.
Can you all hear me? Is that good? Is the voice good? Okay. Thanks, Mary. Let's get started. So, good morning to all of you, or a good night from Bombay. It's unfortunately I'm not there right now due to some administrative processing on my visa front. I hope to be there in a few weeks. Let's see how it proceeds. Anyway, so what I will be talking today is I'm going to go into a deep dive into multiplicity codes. These are a special family of algebraic codes from the sort of family that Mary talked about yesterday. It's my second favorite family of codes. First favorite, of course, being Reed-Solomon and Reed-Muller codes. And multiplicity codes, it's usually described as higher derivative variants of Reed-Solomon or Reed-Muller codes. And basically, it's sort of said that the usual Reed-Solomon code is a set of evaluations of a polynomial. Here, you not only give the evaluations, but also several higher derivative information. So that's the usual way of defined. I'll take a slightly more gradual, non-standard defining these codes. So what we will do in this talk, the talk will be structured this one. We'll spend a fair amount of time motivating and defining multiplicity codes, both the univariate version and the multivariate version. Then we look at one nice applications of the univariate multiplicity codes, which gives rise to list decodable codes all the way up to capacity. Mary spoke about a family of such codes, the folded Reed-Solomon codes. Another family for which we know we can list decode algorithmically up to capacity are the univariate multiplicity codes. We will then see the multivariate multiplicity codes. Particularly, while trying to analyze the multivariate multiplicity codes, we'll also see the multiplicity Schwarz-Zippel lemma, and then see an application of them towards high-rate locally decodable codes. And at the very end, I will talk about various open questions related to multiplicity codes. By the way, this is strange giving a remote talk on this topic. I would like to do this on board. So feel free, stop me. I have a lot of material. If you can see the number of slides, it's 107 slides. So hopefully it's not that long. I can stop at any point of time. So please stop me and ask questions if you have any. Let's make it as interactive as possible, as can be done in a remote talk. Okay. So let's get started. So we're going to, even before to motivate multiplicity codes, let's recall the polynomial evaluation codes. In particular, let's recall these two families of codes which we saw, which Mary possibly talked about in yesterday's lectures, Reed-Solomon codes and Reed-Muller codes. Reed-Solomon codes are the evaluations of univariate polynomials. Reed-Muller codes are evaluations of multivariate polynomials. To be a little more precise, Reed-Solomon codes are of the following type. There's some underlying field, a finite field. There's a degree parameter k. There's S, which is a subset of the field, which is a set of evaluation points. And then there's the message, which is a k symbol string, which is viewed as a polynomial of degree less than k from this field. And then you encode this message by capital S elements from the field. And the encoding is basically, you take the polynomial and write down the evaluation of it at each single location at each of these evaluation points. So P is encoded as P of alpha 1, P of alpha 2, P of alpha n. Short, I'll represent it this way. And Reed-Muller code is almost exactly similar. The only difference now being that you're not in the univariate setting, you're in a higher dimensional setting. So the ambient dimension is some m 2, 3, or a larger dimension. You have a set of points, yes, And you're looking at the evaluation of the Reed-Muller thing on a grid of size S to the M. The field is much larger. The field is much larger. S could be the entire field itself, but we are typically going to look at the evaluation of this multivariate polynomial on this grid of size, on this grid whose sides are all denoted by this set of evaluation point S. And it's exactly the same thing. You take a polynomial of degree at most d, a multivariate polynomial, and you're going to spit out S to the M field symbols. And that's exactly this. You're going to write down the evaluation of the polynomial P at each of the points in this grid S to the M. Yeah, so if you're familiar with this, so quick notion, let's find out what's the distance of these codes. We are very familiar with the distance of the codes. So what goes into analyzing the distance of the codes? For Reed-Solomon codes, we know that the distance bounds come from the degree mantra. Basically, it states that if we have a non-zero polynomial of degree strictly less than k, then the number of zeros of the polynomial is strictly less than k. That immediately translates to the distance of the Reed-Solomon code. For the Reed-Muller code, there's the higher dimensional variant of the degree mantra, which is more popularly called the Schwartz-Zippel lemma, which says that if you have a polynomial of a degree at most d, a non-zero polynomial, then the probability that it vanishes in a grid, that a random point in the grid, the polynomial vanishes at a random point, is at most d times the side length of the grid. That's the Schwartz-Zippel lemma. The Schwartz-Zippel lemma immediately yields a distance bound on the Reed-Muller code. So these are two codes which we're familiar with. Let me talk about one other code before I get on to the multiplicity code definition. It's this notion of folded Reed-Solomon codes. So folded Reed-Solomon codes, these were introduced, at least in the list decoding context, by Guruswami and Rudra. They were introduced in a slightly different context earlier on, but in the list decoding context by Guruswami and Rudra. And these came with, it primarily came for the motivation of Parvaresh Bhatti, who noticed that even though we knew that Reed-Solomon codes were list decodable up to the Johnson radius, and people wanted to know if it's list decodable beyond the Johnson radius. Parvaresh Bhatti noticed that if the evaluation points were bunched up together in some particular fashion, then you could beat the Johnson radius. And the folded Reed-Solomon code was introduced as a particular way of bunching up the evaluation points. And what was the way of bundling up the evaluation points? So we'll have the usual Reed-Solomon code setting. There's a field, a degree parameter, and a set of evaluation points. In addition, we'll have some element gamma from the multiplicative from F star. Typically, it's a generator of the field, but just usually gamma is some element of higher order. And you're going to take the Reed-Solomon code word, which is just a bunch of evaluations, and you're now going to bundle up certain evaluations. For example, we're going to bundle up evaluations which all P of alpha 1, P of gamma alpha 1, P of gamma S minus alpha 1. We're going to bundle up them together and give it as one symbol from the larger alphabet F to the S instead. We're going to bundle up the code. Similarly, this is for corresponding to the location alpha 1. Similarly, you have a location corresponding to alpha 2 and so on. So it is the Reed-Solomon code, but in which you're going to bundle up elements together. And this bundled up code, rather that's why it's called folded. You fold these things one over the other, and you don't give the output alphabet is not a field element, but it is this F to the S. And the folded Reed-Solomon code was introduced and studied primarily for its motivation towards list decoding. In particular, Guruswami and Rudra showed the seminal result that folded Reed-Solomon codes are list decodable all the way up to capacity for certain choices of the multiplicity parameter, yes. Yeah. So what I'll do in this one is I'm going to take a slightly different viewpoint, what I will call the ideal theoretic viewpoint of the Reed-Solomon code, the Reed-Muller code, as well as the folded Reed-Solomon code. So the usual interpretation is the message are the polynomials. Either it's a univariate polynomial in the case of Reed-Solomon or a multivariate polynomial in the case of Reed-Muller. And the encoding is just a set of evaluation. That's the evaluation of the univariate polynomial on all the points in the set of evaluation points, or is the evaluation of the multivariate polynomial on all points in the grid. That's the usual viewpoint that we've taken so far, the standard representation, which I talked about in the previous slides. What we'll do is talk about a slightly alternate viewpoint in which each of these elements, I'm going to view them. For example, let's take the Reed-Solomon code. I'm going to view P of alpha is also the reminder that the polynomial P of x leaves when you go mod the polynomial x minus alpha. It's the mod of when you go mod this ideal x minus alpha. It's exactly P of alpha is exactly that is the value that you get when you divide the polynomial. P of alpha is exactly the reminder when it happens when you divide P of x by x minus alpha. And that's the univariate sort of representation. In the multivariate, you can view P of alpha bar as basically it's the polynomial P of x1. You go mod this ideal. It's an ideal generated by the linear polynomials x minus alpha 1, x minus alpha 2, x minus alpha n. You take out as many possible factors of these. Whatever is left out is exactly the evaluation of it, and you can view it this way. This is a very strange way of viewing Reed-Solomon and Reed-Muller, but it'll come convenient to us in order to introduce the multiplicity codes. Any questions on this? I'm just rewriting our natural representation of Reed-Solomon and Reed-Muller codes as ideal theoretic codes. I'm just writing them as mod an ideal.
Just a quick clarification question. Can you hear me?
Sure, yes.
So when you say the Reed-Muller code, you go mod that ideal. Should that be x1 minus alpha 1 dot xm?
Yeah, sorry. Okay. Yeah, that should be x1 minus alpha 1. Yeah,
thanks.
Right. Thanks, Mary. Thanks. You go mod this ideal. Let's try to do this. So this is that's the Reed-Solomon sort of the ideal view. Let's try to do the same thing for folded Reed-Solomon codes. The folded Reed-Solomon codes, what did we see? There was, you're going to evaluate the polynomial. We're going to write the polynomial as a folded Reed-Solomon code. But in particular, we're going to bundle up the points P alpha, P gamma S minus 1 alpha all together and give it as a symbol from a large alphabet. Now, if we take this sort of ideal theoretic point view, what we are giving here is the polynomial P of x mod x minus alpha, the polynomial P of x mod x minus gamma alpha, and so on up to the polynomial P of x mod x minus gamma S minus 1 alpha. We are giving the polynomial mod several such polynomials. Now, Chinese remainder theorem says that if you want to give a polynomial mod several things, you might as well give for the polynomial mod the LCM of all of those. And in this case, these happen to be co-prime. Therefore, the LCM will be the multiple of them. So this is equivalent to just giving the polynomial P of x mod this larger polynomial. These two are exactly the same representation. If I know the polynomial P of x mod this polynomial, that's the same as knowing P of x mod each of these. Chinese remainder theorem tells you that you can go back and forth. Thereby is due to the Chinese remainder theorem. I want to say this sort of tells you that there's a very general thing in which you give a bunch of polynomials and you can go mod that polynomial. So far, we looked at evaluation codes, which were given a polynomial, give its evaluation at several locations. We could take a polynomial and give its mod several polynomials. More precisely, what I'm saying is we can take this notion of an ideal theoretic code, which is sort of a generalization of the notion of evaluation codes that we have seen, we're familiar with. So let E1, E2, En be n different polynomials, all of exact degree S. And to make it convenient, let's also actually assume they are all monic polynomials. And you want to represent the polynomial P mod these ideals. So what you'll do is you'll give P mod each of these ideals. That's a very natural extension of it's a larger framework in which I can put Reed-Solomon, Reed-Muller, folded Reed-Solomon, all of them under one single umbrella. So you give P mod. So you encode a polynomial by giving it mod several polynomials E1 to En. The question is which of these polynomials, what properties of these polynomials E1 to En make this a good encoding? So we've seen 3 examples so far: Reed-Solomon, Reed-Muller, folded Reed-Solomon. Each of them have some very nice properties. So what I'd like to ask is what are examples of polynomials E1, E2, En such that this encoding is a nice encoding? Is the question clear? Okay. Yeah, and just this one. So what's happening over here is we are taking a polynomial from this space, which is basically k elements from the field, and representing it using n elements, n polynomials, each of degree strictly less than s. So we are representing as n elements from this large alphabet. So the message, which is k symbols, is being represented by n symbols, but from a slightly larger alphabet in this ideal theoretic framework. And a couple of remarks are in order. All, I should mention here, all univariate ideal theoretic codes like Reed-Solomon and folded Reed-Solomon are actually MDS codes. They all lie on the singleton bound. And the entire framework that Mary talked about in her first two lectures, in particular the unique decoding up to half the distance, a la Berlekamp-Welch framework, just extends almost straightforward to this setting. And they almost exists. The verbatim, the same algorithm works for all these ideal theoretic codes, no matter which E1, E2, En you choose. And it takes a little more work, but you can show that even the list decoding algorithm, all the way up to Johnson radius, a la Guruswamy-Sudhan, works. That is, you can take exactly the algorithms which Mary talked about in her first two lectures, and these work for all this entire family of ideal theoretic codes. The Berlekamp-Welch algorithm works up to decoding, up to unique decoding, up to half the minimum distance, and the Guruswamy-Sudhan algorithm works all the way up to Johnson radius for this entire family of codes.
So shouldn't E1, E2?
So what you would like?
I have a question. Like,
sorry, the question.
How can this work for?
Yes, go ahead.
Maybe at least co-prime for this to work. Like E1, E2 should not have.
So the typical case, the examples I mentioned were all co-prime. If they are not co-prime, you are just going mod their LCM, and everything works out. Yeah. But let's assume for now that you can assume, let's say that all the examples we'll be dealing with are co-prime. Let's assume they are pairwise co-prime. So I'd like to ask is what are E1, E2, En, which let you go beyond the Johnson radius, that you list decode beyond the Johnson radius. And we note a few examples, and the most prominent ones of them are the folded Reed-Solomon codes. We already saw what are the EIs in that case. The EIs are these product polynomials. And the multiplicity codes are the ones in which the EIs are exactly x minus alpha I to the power s. So this is what is going to be. The multiplicity codes are ideal theoretic codes in which you're going to go mod, not x minus alpha I as in Reed-Solomon, but x minus alpha I to the power s. I'm going to go mod this and write this down. At least in the case of univariate. For the multivariate, we'll have to do a little more work, but that's basically going to be the code. So let me actually formally define this code. Let's formally define univariate multiplicity codes. Actually, these were defined well before all of this, actually even prior to the Guruswamy-Sudhan algorithm by Rosenblum and Fassman in 97. And subsequently, Nielsen analyzed the Guruswamy-Sudhan algorithm for these univariate multiplicity codes in 2001. So what are univariate multiplicity codes? We have the same setting as in Reed-Solomon. There's an underlying field F. There's a degree K. And now there's an extra parameter, which is the multiplicity parameter, yes. And we have a set of evaluation points, S for 1 to alpha n. The message space is the set of degree at most k polynomials. And the code word space is going to be this. You're going to give the polynomial mod f less than s. In particular, we are going to give p exactly this object. We're going to give p of x mod x minus alpha to the power s. Mod e for each one, for each of the alphas in s. Let's take a closer look at what this operation actually does. So let's see what is p of x mod x minus alpha to the power s. So let's fix a particular alpha in s. it will be convenient to think of alpha to be 0, but this works for all alpha. We'll write P of x in the basis 1, x minus alpha square, and so on. So you can write P of x in the following fashion. I've written the first S terms in this basis, and then the remaining, the higher order terms. And what we really care about is this part. This is what is going to be just this particular, the first one particular symbol of the multiplicity code is going to be P of x. It's going to be the first S terms of this. When I write P of x in this basis, it's going to be the first S terms of it. And should be familiar, this almost looks like the Taylor series. The Taylor series typically has some numbers sitting here. It typically has I factorial sitting here. This is these, so these, and in which case the pi alphas will be the derivatives. But these are, we don't have those denominators sitting there. So these are not derivatives, but something very closely related, and Hasse derivatives. It's actually more convenient to work with Hasse derivatives because if you're working with finite fields, it's unclear if you can do some divisions. So some divisions might be forbidden. So it's actually cleaner to work with Hasse derivatives than regular derivatives. So the pi alphas are Hasse derivatives. They are almost, they share more or less all the properties as the derivatives, except for some scalings. And the first S Hasse derivatives are what constitutes the S field elements that you're going to give in order to represent a polynomial at a particular location. So this is the definition of the univariate multiplicity code. You're going to give P mod x minus alpha. So for every alpha, you're going to give P, the evaluation at that point, the first derivative, and all the way up to the S minus first derivative, and so on for each of the alphas in the field, in the evaluation set. Okay. And I'm going to use this representation short. This is P less than alpha S. Is this combined? Is this entire thing put together? I'm going to call it P less than S of alpha. So this is an element from F to the S. Questions? Okay. And this also will let us this sort of way of writing it will also let us move to the multivariate version of these codes. And it's cleaner because for FRS codes, I don't know what's the natural multivariate version of it. Whereas once you take the ideal theoretic framework, it's very clean to talk about what's the multivariate version of the multiplicity codes. And this multivariate version was introduced by Koparty, Saraf, and Yakanen in 2011. And it's almost exactly the same setup as before. The only thing that's different, we now have just like, it's just going to be what multivariate multiplicity codes are to univariate multiplicity codes, what Reed-Muller codes are to Reed-Solomon codes. It's just you're going to work with a larger dimension. So the only difference out here is this, you have a larger dimension M. And what we're going to do is we're going to give this polynomial P, a degree at most D polynomial in the variable. We're going to give it mod, maybe mentioned, I think. There's a typo here. I'm going to give mod this ideal x1 minus alpha 1, x2 minus alpha 2, xm minus alpha m. I'm going to give it mod this ideal. And the most natural thing is equivalently, you can either think of it as giving it a representative mod this ideal, or you can actually go ahead and write down P of x in the appropriate basis. If you write it to the appropriate basis, that is all possible combinations of the form xi minus alpha I, and then collect all the terms for which the exponent vector is of size at most, of weight at most s. That will be P of x mod x minus 1, x1 minus alpha 1, x2 minus alpha 2, xm minus alpha m to the power s. These are the higher order terms which are going to drop out. So this will be one single symbol of, this is the symbol corresponding to a particular alpha bar. We'll do this for every alpha bar in the grid S to the M. That's how the multivariate multiplicity code is presented. You give this large symbol. Basically, this is going to be a polynomial. I mentioned over here, this is going to be a polynomial from this space. So every the output space, the alphabet is going to be, this is going to be the alphabet of the output space. Okay. So that's so much for the definition of univariate multiplicity codes and multivariate multiplicity codes. Let's ask what's the distance, rate and distance of these codes. Why do we work with these codes? And hopefully they have good rate and good distance. Was there a question? Okay. Yeah, so univariate multiplicity codes, the rate is clear from this one. You're taking k field symbols and outputting small s symbols over this one. So the rate, this should be clear. It should be evident that this is the rate of the code. What about distance? So let's go back to how we found analyzed distance for Reed-Solomon codes. We use the degree mantra for it. And what you need, the degree mantra just says the number of zeros of a non-zero degree less than k polynomial is strictly less than k. This is actually true even if you count multiplicities. So once you take the stronger version, this will immediately give you the distance of the univariate multiplicity code. It gives you that the distance is 1 minus k of s times mod s, and hence this is also an, as said, MDS codes. In fact, all univariate ideal theoretic codes are MDS, and so is the univariate multiplicity code. So this should be clear. What about the distance of the multivariate multiplicity? We're talking about this code in which you're taking a polynomial, a degree d polynomial, and you're representing it mod this ideal. Okay. Notice S equals 1 case is exactly the Reed-Muller case. And there we had argued distance using the Schwarz-Zippel lemma. The Schwarz-Zippel lemma is what came handy to talk about the distance of the Reed-Muller code. So now if we want to argue about the distance of the multivariate multiplicity code, we will need a multiplicity variant of the Schwarz-Zippel lemma. It's just not going to talk about how frequently is the polynomial 0, but with what multiplicity does it is it 0. So we want to count this. So we're going to talk about what's called the multiplicity Schwarz-Zippel lemma, a Schwarz-Zippel lemma which incorporates into it the multiplicity feature. And this actually was first, the multiplicity Schwarz-Zippel lemma was first proven by Dweir, Koparty, Saraf, and Sudan. And let's just state what it is. It's the natural generalization of the classical Schwarz-Zippel lemma to the multiplicity setting. What is it? For this, firstly, we'll have to extend the notion of multiplicity. So for multiplicity for univariate polynomials is very clear. It's just the number of times the polynomial becomes 0. It's the number of derivatives which are all 0. We want to extend this notion to higher dimensions. We'll do it the natural way. If you're working over the reals, it's easy. It's sort of intuitive how you define this. It's this one, but you're working over finite fields. So we're going to define it in the following fashion. So let P be some polynomial and A be some point in the space. And I want to define what is the multiplicity of the polynomial P at the point A. So you're going to look at all the derivatives of it, all the Hasse derivatives of this polynomial. The Hasse derivatives of order 0, which is the evaluation, the first order Hasse derivatives, the second order Hasse derivatives, and so on. You go and keep looking at it. And it's the largest M such that for all exponent vectors, all Hasse derivatives whose order is less than M, the corresponding Hasse derivative is 0. So it's the largest M for which this is true. For the 0 polynomial, M is infinity, in which case you define mult P of A to be infinity. For everything else, this will be a fixed number. It's the largest M such that all derivatives, all Hasse derivatives of order below M are all vanish at this point A. Then this is the multiplicity of this and this one. And so now given this, we can write down the extension of the Schwarz-Zippel lemma. This is the classical Schwarz-Zippel lemma. I just rewritten it as this. It says the expected time that given a non-zero polynomial, the expected number of locations in which P is 0 is less than D over mod S in the grid. The multiplicity Schwarz-Zippel lemma just says, I'm going to replace this indicator random variable, whether a polynomial is 0 or not, by the multiplicity. And still the inequality holds good. So it's a strengthening of the classical Schwarz-Zippel lemma. So this is always less than or equal to this. This is just talking about the first order Hasse derivative. This is talking about as many Hasse derivatives. It says even if you take this expectation with multiplicity in account, that's at most D time D over mod S. When you pick a random point in the grid, S to the n. This immediately gives us the distance of the multivariate multiplicity polynomial. In particular, it says if you take two different polynomials P and Q, which are distinct, we are asking what's the distance of a chord. You're asking how many times, rather 1 minus the distance is how many times are the Hasse derivatives at a point A and at a random point equal for the two distinct polynomials. This is exactly the probability that the multiplicity of the polynomial P minus Q at the point A is at least S. And Markov will tell you that this is at most D by SS, and hence we have that an immediate corollary of this is the fact that the distance of chord is at least 1 minus D over S. You gain this factor S over the usual Reed-Muller code. Questions so far? Okay. So what I will do, we'll see two about the 30 more minutes. What I'll see and do in the remaining 30 minutes, we'll see two applications of these codes, one for the univariate setting and other for the multivariate setting. And this univariate setting will be very similar to Mary's lecture on list decoding multiplicity codes. We'll ask. So one of the big reasons univariate multiplicity codes were studied in coding theory is because they are list decodable well beyond the Johnson radius. In fact, they are list decodable for certain choices of the multiplicity parameter all the way to capacity. More precisely, Koparty and Guruswamy Wang independently considered the following problem. That is, you're basically given the list decoding problem is the following problem. You're given a reseed word, which is basically you're given for each of the n evaluation points, you are given this symbol from this large alphabet, beta I less than S, which is you're given this symbol. And you want to find all degree D polynomials P such that which have good agreement with the given reseed word. Basically, you want to find this, have agreement at least T. That's this one. If this was the distance by 2, this is a unique decoding, and we want to find as small a T as possible. And if T, we can make it all the way up to 1 minus R S plus 1, that's says it goes up to capacity. So that's the question we want to look at right now. This is a list decoding question. We want to study univariate multiplicity codes from the viewpoint of list decoding. Is the problem clear? And then I'll get on to the sort of solution, the algorithm which we have, which will be very similar to, which will be identical to the sort of linear algebraic framework that Mary discussed in yesterday's lectures. Okay. And so Koparty and Guruswamy Wang independently, they gave slightly different algorithms, but essentially they showed the following. They showed that for every rate R and epsilon, there is a multiplicity parameter S, there's a large enough S, such that the univariate multiplicity code with degree D, block length N, multiplicity S, and rate this one over fields of characteristic at least D times N is list decodable from so many fraction of errors. This basically says that list decode univariate multiplicity codes of large enough multiplicity are list decodable to capacity. Okay. And before I sort of try to give a high-level idea of how this statement is proven, I want to just stare at this theorem statement, say that it doesn't, by the way, it doesn't show that all univariate multiplicity codes are list decodable up to capacity. It only says if you want to come epsilon close to capacity, then you need the multiplicity parameter to be suitably large enough. So it says if you, depending on how close you want to come to capacity, it gives you a particular family of univariate multiplicity codes which are list decodable all the way up to capacity. That's one caveat. It doesn't show all univariate multiplicity codes are list decodable up to capacity. Two, and the bigger issue is, the current proof has the caveat that it works only if the underlying characteristic is large enough. The definition of univariate multiplicity codes did not care about characteristic. but at least both the algorithm, both the Koppati algorithm as well as the Guruswami-Wang algorithm, both require the analysis sort of breaks down if the characteristic of the underlying field happens to be small. It needs a characteristic to be large enough for the proof to go through. So this is a caveat of this. We don't know. So this is actually an open question out here. What happens to univariate multiplicity codes when the characteristic is small, and what happens to other multiplicity parameters, smaller multiplicity parameters? Do we know how to list decode them beyond the Johnson radius for these settings? We don't know the answer to this question. Okay, so that's the statement of the theorem as we know. So any questions before I move to give a sort of a high level view of how this theorem is proven?
I have a question.
Yes.
If I want to reduce field size, do people ever consider subfield subcodes of these to like, because you're blowing up the field size by S to try and get it back down?
So you're not the field size, you're talking about the alphabet size.
Yeah.
So no, so what was your suggestion? What was your, this one,
So-
whether to?
People have considered subfield subcodes, like when you go from BCH, Reed-Solomon codes to BCH codes, you can also take subfield subcodes.
So usually what's done, okay, so that you could ask for this. I haven't seen such sort of work. That's interesting. I haven't seen such sort of work. Usually what's done to get back to code, this one is constant size alphabet, is you do concatenation and reduce the alphabet size and analyze how the list decoding algorithms work under concatenation. I haven't seen the BCH version in this context. And also, I haven't seen it. It'd be interesting to see such things. Okay. Proceeding to the algorithm. Okay. So, and the algorithm is going to be, we're going to follow, by the way, there are two different algorithms for this right now. Very similar, but two different algorithms. One is the algorithm due to Swastik Koppati, and the other is to Venkat Guruswami and Carol Wang. And as Mary did in her talk, we will follow the linear algebraic framework of Guruswami and Wang while describing the solution. There's an alternate solution due to Swastik. It has certain advantages over this. It's more complicated, but has certain advantages. We'll not get into this. I might try to answer that, address that later on, either in the open questions or later on, the differences between the Guruswami-Wang algorithm and the Swastik Koppati and Koppati's algorithm. So how do these things work? So it's like the Berlekamp-Welch algorithm or the Guruswami-Sudhan algorithm. The first step is somehow find an algebraic explanation for the entire received word. Somehow we find an algebraic representation. What is this algebraic explanation? We basically find some polynomial. In this case, it's some m plus 1 variate polynomial. We're introducing new variables y0, y1, y2, ym minus 1. This m is some number between 0 and s minus and s. S is the multiplicity parameter, remember. It's some number between these two. And q is some polynomial of this type. It's a polynomial which has a of x plus summation I equals 0, yi times d of x. The crucial thing to notice is the degree in each of the yi's is 1. The degrees in A could be large. There are some degree constraints on A's and the Bi's. I'm going to skip that for now. It will be evident in the next few slides what are the degree constraints I need to put in. We're going to find some polynomial that satisfies a bunch of conditions. All will be linear conditions in the coefficients of A and B, A and the Bi's. Instead of describing what the conditions star are, what I will tell you is what do we need from these conditions, and then it should be evident what these conditions star are going to be. So what do we want from this? We want the following thing. We want that the conditions to be such that if suppose there's some polynomial P and the received word, suppose they happen to agree at a particular point, say at the point alpha I. So the polynomial P less than and beta less than, they happen to agree at this point. The conditions that we impose should be such that if you look at the polynomial R of x, which is, take this polynomial Q, which I defined over here, and plug into it, instead of the yi's, P of x, the first derivative of P of x, the first has a derivative, the second has a derivative, all the way up to the m minus 1 has a derivative. If you look at this polynomial, which I defined this way, this polynomial should have a root at the point alpha I with multiplicity s minus m. The conditions basically are just to make sure that this is the case. These are a bunch of linear constraints, each constraint telling you that this order derivative is 0, this order derivative is 0. And the condition star, 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 exactly these conditions to ensure that if these two happen, then this polynomial R of x has a root at alpha I with multiplicity s minus m. And why is such a condition useful? Now, suppose P was a polynomial such that P and the receive word agreed not just at this point alpha I, but at t such points. That would mean that this polynomial R of x that we have defined this way has s minus m times t roots. That's counting with multiplicity. For each of the t points of agreement, it gets in a 0 with multiplicity s minus m. So therefore, the polynomial R of x has s minus m times t roots counting with multiplicities. And in particular, if we had set the degree parameters for a and bi such that the degree of this polynomial happens to be less than s minus m times t, we get that R is identically 0. So the degree parameters are set such that when you plug in P, P1, P2, Pm minus 1 into Q, these are at most degree 1. This is a degree k polynomial, this is a k minus 1 polynomial, k minus 2, all the way up to k minus m minus 1. If you plug in this, then the resultant polynomial has to be of degree at most s minus mt. We set it up so that this is the case. Then R is identically 0. In other words, for every point polynomial P that has significant agreement with the received word, we will have that this polynomial, when you plug in P of x, P1 of x into Q, P will be a solution to this. We get a differential equation of which P will be a root of. In particular, so we're going to have the following. We find an algebraic explanation. So for R in particular, we'll find a polynomial Q x y naught ym of this form satisfying these conditions. And these conditions are exactly the conditions that are required to make this happen. You can check this out. These are just linear conditions. These are just linear conditions. It's a bunch of linear conditions. We write just one after another. We write all of them down. And that's step 1. We're just going to find a polynomial Q with certain linear constraints satisfying this. There's a bunch of homogeneous linear constraints. If the number of variables is more than the number of constraints, then there is a solution. So you just pick one such solution. That's how it goes. That's how this proceeds. I'm not writing explicitly what star, star, star is. In fact, it's not very insightful knowing what it is. All that you know is the star, star, the conditions star, star, star are the conditions that make this observation go through. Whatever makes this observation, just write that down, and that's what this one is. Now, once we have this, we have from the previous step that every root, every close enough polynomial is a solution of this differential equation. So step 2 should just be, we now have to solve the differential equation. We have the polynomial Q. We have to find all polynomials P for which this is identically 0. We have to solve this differential equation. This is different from what Mary had suggested. In Mary's this one, they were not differential equations. They were just Q of x comma P of x. They were just factors of the form. You had to find factors. Here we have differential equations that we need to solve. But the way to solve them is exactly the same. You just similar to factorization. You first write this equation mod x, find the constant term, go mod x square, go each of them, write it down, write down what should P be. And you notice that the solution is just, you'll get a bunch of linear equations and you have to solve the system. In fact, if you write it carefully, it will be an upper triangular system and it'll be extremely easy to solve it. The solving this differential equation is not a hard task at all. You just write down what this condition means. If you write it on this one, it will be an upper triangular system in the coefficients of P with just m degrees of freedom. And so once you fix the first lower or small coefficients for P, you can complete the upper triangular system. Will tell you now there's a natural way to satisfy the differential equation. You solve it and that's it. So step 1 and step 2 are this. So step 1 finds an algebraic explanation for the entire received word. Step 2, and because with the way step 1 has been done, it ensures that every polynomial which is close enough to this satisfies a particular differential equation, and then you solve this differential equation. That's step 2. And both are in the Guruswami-Wang approach, they are linear. They're both linear algebraic solutions. This is solving a homogeneous system of linear equations. This is not a homogeneous system, but if you write it down carefully, this will just be an upper triangular system, and it's very easy to solve this. Okay. Any questions on this? Otherwise, I'll say a couple of remarks and what's happened since the algorithm of Guruswami and Wang. The first thing to notice is what I said now is a fully deterministic algorithm. It's a bunch of Gaussian, solving various Gaussian systems that list decodes the capacity and will output lists of size q to the m. And why is it q to the m? You just notice that there's an upper triangular system in which there are m degrees of freedom. Therefore, once you fix the m degrees of freedom for this, not evident from here what's the m degrees of freedom, but you can check that it has m degrees of freedom, at most m degrees of freedom. Once you fix that, the entire polynomial p is fixed. Therefore, the utmost q to the m polynomial. So this algorithm, which I suggested in the previous slide, actually gives you a deterministic algorithm that list decodes the capacity and outputs lists of size possibly as large as q to the m. You can further, of course, prune these things. You can throw away polynomials which are not close enough, but it will give you lists of size at most as large as q to the m. And this is an efficient algorithm. Subsequent to this, actually in very recent work, about 5 years ago, Kopati, Ronzevi, Saraf, and Wouters observed that the list size actually can be reduced considerably from q to the m, which seems to be a polynomially large function. They show that you can actually reduce it to a constant. The constant sum, depending on how close you are to capacity, order epsilon 1. This is a randomized procedure. They just showed that basically if it was using the observation that here, this algorithm output polynomials which are all solutions sitting in an affine space, and they showed that a code with good distance cannot have a lot of code words in an affine space. They can't have q power m code words. It will actually be much, much smaller. And they gave a randomized pruning algorithm to reduce the list size from q power m to order epsilon 1 to a constant size list. And it's a randomized procedure to do this. It'd be interesting to actually get a deterministic counterpart to the pruning algorithm of Kopati, Ronzevi, Saraf, Wouters. More recently, earlier this year in joint work with Goyal, Kumar, and Shankar, we showed that actually this algorithm, which was solving various Gaussian systems and seemed to be actually polynomially, it used to runs in times at least n cube, can actually be made to run in quasi-linear time. It can be made to run in order n polylog in time. That is, you can carefully look at step 1 and step 2 and notice that actually the systems that they solve are very nicely well-behaved systems. And you can reduce the running time from poly in n to n polylog n in running time. By the way, all of this which I said right now, this set of framework works for the folded Reed-Solomon code word. Both the pruning algorithm as well as the nearly linear time works for the folded Reed-Solomon. Any questions on? That's sort of what I wanted to say about univariate multiplicity codes and their list decodability all the way up to capacity. I haven't gone through the parameters, but once you have this algorithm, you write it down and you can show that there is a particular choice of S and M for which the corresponding univariate multiplicity code will go all the way up to capacity. Okay. So another 10 minutes, what I will talk about is the other very nice application of multiplicity codes. This time the multivariate counterpart is the local decoding of multivariate multiplicity codes. Is there a question? Or? Yeah. In particular, and this is sort of Reed-Muller codes are known to be local decoding or locally decodable. In particular, if you want to locally decode a Reed-Muller code, you're given a noisy Reed-Muller code word. How do you locally decode it? At a particular point location, you pass several lines through it, take the majority voting, and hope that this would work. And many a time this works. And we would like to ask, is a similar thing true for multivariate multiplicity codes? Why do we care for doing this? And in fact, this was the original motivation of Kopati, Saraf, and Yakanan when they defined multivariate multiplicity codes. They defined multivariate multiplicity codes precisely for this reason, for their application to local decoding. because the Reed-Muller code, which I just mentioned, it's locally decodable, but locally decodable with sublinear query complexity. But on the other hand, the rate is never more than a half for Reed-Muller codes. The Reed-Muller codes rate stops at half. So you never get high rate codes which are locally decodable. And it was open for a long time whether there exist codes which have rate better than half. In fact, rates all the way close to 1, which are also locally decodable with sublinear query complexity. And Koparty, Saraf, and Yakanen actually discovered multivariate multiplicity codes precisely for this reason. They showed that for every epsilon and alpha, epsilon is how sublinear you want to be. Alpha is the rate of the code, how close you want it to be 1. And any dimension k, there are multiplicity codes of dimension k, rate 1 minus alpha, and locally decodable from constant fraction of errors in sublinear amount of time. So the improvement over Reed-Muller comes in the fact that they can handle rate going arbitrarily close to 1. You tell me how close you want to, and I will give you how close you want the rate to be to 1 and how sublinear you want it to be in this one. And I will give you a code, and I will give you a multivariate multiplicity code, which is locally decodable in that sublinear time and with rate 1 minus alpha. Okay. This was the original motivation of Koparty, Saraf, Yakanen when they introduced multivariate multiplicity codes. Subsequent to their work, of course, there have been several alternate constructions which also satisfy this, which also yield the same sort of construction. They are different codes. These are not multivariate multiplicity codes. In particular, Gyo, Koparty, and Sudan and Gyo showed that there are certain family of affine invariant codes which have this property. Hemingway, Ostrowski, and Mary showed that there are certain codes based on expander codes which can also have, which are locally decodable, high rate locally decodable codes. But what we will see, what I'll give you a very high level bird's picture of why multivariate multiplicity codes do achieve, you're able to locally decode from them. Was there a question?
Yeah, well, maybe just to clarify, so taking epsilon really small, if I make it say sub constant, I guess the term your constant you're hiding in the big O will blow up.
So the constants I'm hiding here will basically use this.
So it could be like k to the 0.01, but not k to like 1 over log n or something.
I don't think you can make this poly log k. This algorithm gets. You can make epsilon to be slightly sub-constant, but I don't think you can make this sub-constant to go all the way small to polylog k from where the parameters look at. I'm not. You can't make it polylog k. That I'm definitely sure of it. But you can certainly make epsilon to be something slightly sub-constant. It can be a little low one number. Yeah. Okay. So once again, what's the problem here? So we are given some word, we are given some f on the entire space. Basically, for every point in the space, f to the m, we're now looking at multivariate multiplicity codes, which are defined on a grid, and we're going to assume the grid is the entire f to the m now. We are given basically for the entire f to the m, we are given for each location, we are given a polynomial of degree at most s over there. And we are told that this function is actually close to some encoding of an honest to God multivariate multiplicity code. In other words, there is some polynomial p of degree at most d, such that if you pick a random, such that f and p disagree on a random location is at most delta naught probability, and delta naught say is less than delta by 8, where delta is the distance of the code. And you're then given a point alpha in the whole space, and you want to find, what you want to find is actually the value of the closest code word at the location alpha. That's what you want to find. Pictorially, what you have is this, that is you're given this table of values for every point in this grid, in this space, you're given a polynomial. And there's a bunch of locations, say this violet shaded area, where it's erroneous, but you don't know this region that's erroneous. You're given f here, You promise that its f is very close to some p. You do not know where the errors happen. And then you're given a point alpha, say this point alpha. It's possibly you do not know if it's an erroneous point or a non-erroneous point, and you want to find the closest code word at the location alpha. That's the picture we have. So we have f like this. There's an error set over here. Error set is promised to be not too large, but we don't know where the error set is, and you need to find out. And you're given an alpha, which could be in the error set or elsewhere, and you need to find out p of. You want to find the closest code word at the location alpha. How many more? I have about 5 more minutes, Mary, or?
Yeah, something like that.
Yeah, okay. Let me so quickly tell what's going to happen here. So the algorithm designed by Kopati and Saraf-Yakanan for this with further modification. Actually, what I'm going to give is the algorithm due to Swastik, Kopati, and a subsequent modification of the KSY algorithm is as follows. So the natural thing to do is going to be very much motivated by the Reed-Muller thing. We are going to shoot off lines through this point alpha. Look at the restriction of the multivariate multiplicity code to these lines. You're going to get univariate multiplicity codes. You're going to decode them. And then put those information together to be actually able to decode at the point alpha. Now, how do we choose? We need to figure out which are the, we want to choose a large set of nice set of lines. So the way the case, sorry. So the way the set of lines is chosen in the following fashion. Let S be some large set of this ones, which is of size 10s square. Notice S is the multiplicity parameter. So this is just a large constant. S, we think of it as a constant. You go to some high order multiplicity. It's a constant. So it's just some large subset size of the field. The field could be growing in N, but this is just a constant size subset of the thing. You pick randomly A, B1, B2, Bm, the things in the field in the S space F to the M, and you pick this collection of points B, which is basically A plus summation Ri Bi for Ri's being in S. Notice that for a typical choice of B, the size of B will be S to the M. If there are no linear dependencies, and so if you're lucky for this one, they won't. What happened? I don't know why my screen stopped sharing. Just give me a second. You choose the set of points B. And what we will do is for each beta in B, we'll shoot a line in the direction beta through alpha. We're going to shoot this line this way. We're going to shoot this line beta through this. And we'll obtain the restriction. We'll query so we're going to query it on several such lines. We're going to query the code word on several such lines. And you're going to get, you'll get the restriction of the multivariate multiplicity received word on this line. This most likely, because these lines are chosen at random, it's most likely there are going to be very few errors, and you can, for a good fraction of the lines, you will actually be able to decode the corresponding univariate multiplicity code fully faithfully. You'll be able to do the list decoding, assuming you can do decoding of univariate multiplicity codes. So in particular, you will get this polynomial Q beta ET, which is a polynomial in just this direction. Now, so for most choices of our randomness, at least 2/3 of the lines that you shoot in, you'll have that this polynomial Q beta ET is actually the corresponding Hasse derivative of this one. This is just, forget about notation, you will actually honestly be able to get the univariate multiplicity code along that direction. Now from this, I want to recover what is PE at alpha. Notice it, we only have PE at alpha plus beta t. And you do not know which of the points are correct, which lines are correct, which lines. You know that 2/3 of the lines are correct and stuff. So what we'll do is we'll look at just look at this polynomial. Look at this polynomial, just look at the coefficient of t power j in the above polynomial. You get a polynomial in the variables beta. You get the coefficient of this is going to be something in the variables beta. and beta are the choices. And if you notice it, the polynomial that you get will actually be a degree S polynomial. It's M variate. And it's exactly a multiplicity encoding on the set B which we had defined over here, which looks like a grid S to the power M. So this is a smaller such problem of the same type, but on a much smaller degrees of size. Yes, it's a constant degree polynomial. It's the same problem, but a constant degree, and you have the entire information here. You can do sort of a global decoding for this and recover PE alpha. I'm hand waving a lot, but this is essentially the entire algorithm of Koparty's. Koparty's improvement over KSY is exactly this. You shoot several lines, you infer the univariate multiplicity code on these lines, and then you look at them, you want to put these information together, you realize that what you have is actually a constant degree M-variate multiplicity encoding on the set B, and that you can do some global decoding to recover it. And that's the entire algorithm of it. Then you set the parameters correctly, you get the theorem I stated. Okay. What I will do in the next few minutes is just wrap up with a few open questions. Multiplicity codes, I really love this set of family of codes. There have been a lot of nice questions. Let me start off with questions related to decoding. The first questions related to decoding are related to actually the questions I talked about. What exactly, just like Reed-Solomon code, what is the list decoding radius of multiplicity codes? We know that they can all be list decoded up to the Johnson radius. For certain choices of the multiplicity parameter, it goes all the way up to capacity, but only if the characteristic is large enough. What happens to the other multiplicity parameters and for other characteristics, this is open, but this possibly is intimately tied with what happens in the case of Reed-Solomon code words. That's for univariate. For multivariate, in fact, we could ask, can we even do unique decoding algorithmically? There have been partial results which sort of answer this recently, due to building on work due to Kim and Koparty, and also whether you can do list decoding. All of these results are not completely satisfactory. They only show it for certain choices of S. We can do unique decoding all the way up to half the minimum distance. We can do list decoding on grids, but they don't answer this question completely. So it's widely open how to do for multivariate, do unique decoding up to how even unique decoding. We don't have an algorithmic thing for all parameters of S. And list decoding, I'd like to ask up to Johnson radius do we have? We don't yet know how to do this for the multivariate setting. Next question which you can ask is, given such a code, are these, we showed they were locally decodable. Are they locally testable? Like Reed-Muller codes, are they locally, Reed-Muller codes have been should be locally testable, and this has been used for PCPs. It would be interesting if multivariate multiplicity codes are also testable, then they possibly have some PCP applications. They've been, once again, this is a very, it's not an area that's been well explored. We don't have any results. There have been recent results due to Karliner, Salama, Tashma, and Karliner and Tashma, who show that the line tester is not a good test for multivariate multiplicity code, but possibly the plain tester is. But this doesn't yet still answer the question completely. It doesn't answer the question as well as we know for Reed-Muller codes. Could then ask, are there other applications? Reed-Muller and Reed-Solomon have a zillion applications in coding theory and are they elsewhere in theoretical computer science? Do multivariate multiplicity and univariate multiplicity codes have applications? Recently, once again, Tashma Amnon has been working on this multiplicity codes quite a lot in the last couple of years. In joint work with Kalev, he shows that you can sort of build unbalanced expanders, and in particular, recover the result of Guruswami, Umans, and Vadan from multiplicity codes, from univariate multiplicity codes. It'll be interesting to get more results. Yeah, I don't know. I'll conclude with this. Thanks. We should remark that most of my talk was based on this survey article by Swastik from 2014, except for the results that came subsequently to it. It's a very nice article by Swastik, some remarks on multiplicity codes. I'll stop with this.
Maybe we have time for one quick question.
Thanks for the nice talk. Out of curiosity, can you adjust the local decoding algorithm to get a local list decoding algorithm? If instead of just local decoding along lines, you just run like Guruswami 1 list decoder?
Yes, you can. Yes, you can. Yeah. This is, yeah, you can do it. You can do exactly what you did for Reed-Muller codes in this context also. I don't know, I don't recall off the top of my mind how well are the parameters, but you can do what one does for Reed-Muller even for multivariate multiplicity codes.
Can I actually ask one more question as well? Okay, thanks. I also have one other kind of silly question maybe, but I'm curious. So the way you said that, you can go from univariate multiplicity codes to multivariate multiplicity codes just by picking the appropriate ideals. Could you do the same? Has anyone tried doing the same game with like a folded Reed-Solomon codes? I guess you would have to then just have m different variables, and then you would have like, you would take the ideal x minus gamma to the j alpha I for j going from 0 to s minus 1 and I running from 1 to m. Has that been looked at all, or is that even?
So there have been works which looked at this. There have been works, but none of them seem. It doesn't. I haven't. So they've been work more from in the arithmetic complexity theory, where they've been trying to design pseudorandom generators and stuff. This context, they have considered for multivariate versions of folded Reed-Solomon codes, but somehow they have the results are not as clean as one gets from multivariate multiplicity codes, and it's properly because the choice of ideal is not the right one, or we don't yet understand it, or this one. But this has not been explored well enough for that. If you're the multivariate, I don't know what is the right analog of multivariate analog of FRS codes, and what do they give you? It's also not clear.
Let's thank Prahladh again for the great talk. And as usual, we're